Okay, great. Hi, everyone. Welcome to the SimCenter Community Roundtable meeting. My name is Matt DeJong. I'll be hosting the meeting today, along with Professor Luis Ceferino from the University of California, Berkeley. Thanks a lot for joining us today and talking with us about simulating power infrastructure. This particular roundtable is hosted by the working group at SimCenter on regional simulations for lifelines and transportation, which is the working group that I'm currently leading. You're probably aware there's 5 main working groups that we have at SimCenter, and each of these has developed some community roundtable meetings. So please do look at our website and look for the other available meetings as well. We have a really exciting list of presenters today for this particular roundtable. I'll introduce each of them as we get to their presentations, but this will be the order of presentations. We'll have 4 presentations in total. And then at the end, we'll have a panel discussion and a group discussion where we're all welcome to contribute, which will be hosted by Luis Ceferino. Just to share the objectives of these roundtables, for those of you who this might be the first one you've attended, the purpose is really just to share recent advancements of different researchers in the field. So it's not just SimCenter advances. One presentation will be SimCenter focused. The others are just leading experts in the field. The goal is to foster research collaboration, to see what others are doing, see how we can work together. Also to inform the community a little bit about what we're doing at SimCenter and different tools we're developing and how we might be able to support your research. And then finally, to have an open forum to discuss computational needs and challenges in various fields related to natural hazards. So that's our objective for today's meeting. Just so you know, as you're going through during the meeting, you're welcome to participate using the Q&A button in the bottom. So the participants at first will be muted, but if you have a question, use the Q&A button. And then from presenters, you're welcome to answer those Q&A questions, probably not while you're presenting, but while other people are presenting. If you want to answer, you're welcome to. And then we'll also circle back to those Q&A questions at the end when everyone's done to have a bigger discussion if there are larger topics that multiple people want to comment on. You're also welcome to drop real-time discussion in the chat if you would like to, but we won't be monitoring the chat as well as we'll monitor the Q&A. Again, during the discussion, we'll start by Luis will host that. We'll start with looking at Q&As that we've received, and then at the end, we'll open it up for participants to raise their hands and participate verbally as well. So that's our plan for the day. Just at the beginning, I want to just mention at the outset how you can stay involved or be involved in SimCenter if you're not already. If you go to the Join Community tab on our website, it's the best way to see different ways that you can be involved. Subscribe to our newsletter. You're welcome to join the working group meetings as well, where we discuss our plans for developments within SimCenter. If you'd like to join one of those working group meetings, there's contacts on the website you can contact. There's also a GitHub discussion forum, and these community roundtable meetings we're planning to continue several times per year, so look out for future ones of those. Also, there's a couple of upcoming events you might be interested in. There's a SimCenter workshop at the Wind Engineering Conference coming up in May. 2 weeks of online boot camps this summer for programming. And then there's a new initiative called SPARK, the NEARI Strategic Program to Accelerate Researchers in Computing. That's in July at UT Austin, where people wanting to use SimCenter tools and get assistance with that, as well as DesignSafe can join. Okay, with that, I'll stop sharing my screen and we'll move right over to the presenters. So our first presenter today is Professor Paolo Bocchini from Lehigh University. Among other things, he's the director of the Center for Catastrophe Modeling and Resilience. And Paolo, I'll pass it over to you for your presentation.
Thank you. Thank you, Matt. Can you guys hear me? All good?
Yeah. Yep, we hear you. And your slides look good.
Perfect. Okay, so I have set up myself for a difficult task because normally we have 15 minutes when we give a deep technical presentation, or something like 1 hour when we give a seminar, a keynote, etc. Here, I try to combine some messages, like if we were giving a lecture, but condense it in 15 minutes. So I'll do my best, and I'll be a little superficial because I want mostly to go over some concepts than specific methodologies. So these are the main topics I want to cover today. The first one is some very, very brief highlights on some things that we have done in terms of advancing simulation of power lines under hurricanes. Then I will show you some results on whether it matters or not to push the envelope in trying to refine these models. And finally, I will cover some aspects of class validity models that we're working on right now. So let's start with the first. And I like to show this slide that gives a general idea of the approach that we have had for almost 10 years at this point, when we developed fragility and vulnerability models for this type of lifelines. The most important thing and the most important challenge, in my opinion, is to understand how you need to span a very large range of scales. For some of the structures involved in these problems, the bolted connections are really governing the dynamic behavior and need to be captured well. So you need to start your study by looking at things that are in the scale of millimeters, a fraction of an inch, and then work your way out, work your way up, always carrying all the important information with you and dropping everything that is not as relevant, all the way to studying the functionality of these systems that really makes sense when you have a model that spans hundreds of kilometers or hundreds of miles. So there are something like 8 orders of magnitude that you have to span in these models, as well as really different disciplines. You have to go from continuum mechanics to structural mechanics to system fragility analysis, and finally power system analysis. So some examples, I like to start with our work on lattice steel towers. One of the big challenges, as I said, is to capture well the behavior of these bolted connections. And we had to work starting from experimental data to create 3-dimensional finite element models that could well represent the static and dynamic behavior of these bolts, and then go from those finite element models to simplified analytical models that we could eventually embed in an OpenSeas element and put it into our tower models. To tell you something funny, we had absolutely no idea that we had to do this when we started working on these towers. Our plan was to go directly to the tower model, and we realized that to really capture this, we had to start with this entire preliminary work that took something like 1 year. Once you have the tower model, you need to apply your loads, and other students in our team had worked on the development of wind load time histories correlated along the height of tall, slender structures, and so we could leverage that work and apply direct wind loads to our towers. But then another issue arises, and it's what happens with the load transferred by the conductor cables. Of course, we could simulate all the loads applied to each point along the conductor cables, but that would generate an incredibly complex correlated set of loads that was really impractical to handle. So instead of using this naive approach, we decided to study what happens if we could, in a way, linearize the problem. And of course, the idea of linearizing the dynamic of these cables seemed crazy at the beginning. But if we could linearize it and use model superposition, then we could really calibrate a spectrum for the reactions of the cables to the attach points at the towers. And it turns out that if you choose the right point around which you do the linearization, you can actually do this with very, very high accuracy. So do first a preliminary mapping to a more convenient state, and then do the linearization. Similar issues apply when you want to compute the fragility of the cables, for examples. And again, here we wanted to check if it was possible to linearize this problem, and we figured that if you do it around a condition where the cable is already loaded by the mean wind, then the stiffness of the cable doesn't change very much. And so you can use a sort of model superposition approach and still get very good results. So with that, we ended up with fragilities for the towers, fragilities for the cable as a function of the wind velocity and as a function of the angle of attack of the wind. For the towers, one element that is often neglected is to select the right engineering demand parameters to consider. The most common approach in this case is to study the tip displacement as a metric of the global behavior of these structures. But in reality, the failure of these structures is not really governed by their global behavior, but more by specific local buckling of some of these elements. So we quickly realized that we couldn't get good results just looking at the global deformation. We had to look at specific levels of stress in each element and then do a sort of progressive collapse analysis to study the fragility of these towers. We also looked into transmission monopoles, so other types of transmission line support structures. We started by calibrating fragilities using the most common approaches in the literature that are based on the assumption that the highest bending moment occurs at the base of these structures. And so you can do effectively a static equivalent analysis, compute the capacity of these poles at the base, and apply the equivalent bending moment coming from the hurricane wind. And we ended up computing fragilities with these assumptions for different classes of these poles, etc. But then we noticed that the assumption that I just mentioned of failure at the base works very well for distribution poles, but it doesn't work as well when you're dealing with bigger structures used in the transmission lines. Unfortunately, there are a lot of failures, probably more than those occurring at the base, that happen midway through the height of the tower. And as many of you perhaps have already guessed, this is due to the fact that the second mode of vibration tends to excite and generate bending moments that are higher around the middle of the height of the tower. And especially considering the fact that they are typically tapered and there are additional connections that can exacerbate the loads at some locations, these end up being the most critical cross sections. And so we're creating now a new set of fragilities that includes also these possible types of failures. Very briefly, where do we use all of these different structural fragilities? Well, we use them for entire analysis, as I hinted at in the first slide. We have hurricane simulation models that give us tracks and wind fields over time. And we can apply, we have a highly detailed model of some transmission lines, knowing exactly the direction, the location, and the connectivity for something like 6,000 transmission towers and a lot of conductor segments. And we put all of this in this general framework to eventually calculate the probability of failure of each of these towers. But also in this case, I will bring up another crucial challenge, that is the necessity to decouple the uncertainties that come from the load and those that are proper to the structure. When you are simulating an event with a certain duration in time, like a hurricane, You want to sample your structure only once at the beginning of the hurricane and keep all those properties sampled exclusively once and remain constant through the passage of the hurricane, whereas you want to sample the variability in the load all over the duration of the event. So this is against the traditional way in which fragility curves are built, right? Normally we put together uncertainty in the load and in the structure, and we create a fragility that gives us a combined probability of failure. So we had to find a way to decouple these two different sources of uncertainty for this specific class of simulations. And I will not go into the details, but I'll be happy to point to some references. As a result, we can compute the probability of failure of every transmission line. We can compute the overall ability of the tower to deliver, of this network to deliver power to their users. And we can also include the recovery models to show how the unmet demand evolves over time. So the second question is, do we really need all of these advanced models? Because the truth is we have a good number of fragilities that are available in the literature. We know they're approximate, they make a lot of assumptions, but does it make a difference when we study the overall system performance? So I have another student who started looking specifically into this type of problems. I'm very happy to see that there is more awareness for these meta questions in the community. We started asking these questions about 10 years ago. I've seen now students dedicating an entire PhD dissertation, for example, at Rice University, to address this type of questions. So what this student did was studying the power and transmission network in Florida and do a series of sensitivity analysis studying a lot of different conditions. Here, I will show only two comparative studies. The variables that we have included are things like the tower characteristics, the specific distribution of the towers within the portfolio, the wind direction, randomness in secondary variables of the tower and of the load, and spatial correlation of failures. So the first result that I will show you is this one, where we were keeping most things constant and changing the percentages of two archetype towers. So in this case, the distribution of the towers in the network is kept constant. There is only one map for each one of these cases, but we're changing the percentage of towers of type A that ends up being a little bit stronger. And you see that we have a very substantial shift in the distribution of the functionality at the end of the event. Now, consider that we're looking at the functionality of the entire state, but the event really hit only a portion. So a variation of something like 5-6 percentage point is a huge variation for that particular area. However, if instead we change the location of the towers within the power lines, we see that in this case, the variability is much smaller. See, the horizontal scale has changed, and these interquartile ranges are really tiny. The largest of them is less than 0.6%. So it means that we really need to capture all the variability that we observe in the portfolio, but it doesn't matter very much that we locate it at the specific towers that are in the system. So this conclusion leads to the third and final part of the talk, that is the fact that we have to look for surrogate models that can capture this variability, but don't require us to know specifically the properties of each tower, that are parametrized class fragility models. Now, models of this kind have been around for a very long time. They mostly started with the study of bridges. And I think that one crucial step that was done at the time was to be able to simplify a very complex structure like a bridge into a series of very simple elements that could capture entire blocks of this structure. Nothing like that was done in general for transmission towers, right? The fact that towers tend to be a little bit simpler led to the conclusion that we could model each one of these elements. But that's not true if you want to capture this structure-to-structure variability that you have in classes. So a few years ago, one of my students set out to do a similar transition and calibrate models that, in this case, the unit for these models is the panel of each one of these structures, so that we could create surrogates that could capture entire classes of these support systems. Now, I'm running out of time, so I will not go into all the details of how to create true mechanical equivalence for these surrogate models. I will just point out the fact that one of the biggest challenges was to be able to capture in a way that is coherent the stiffness provided by a specific sample of a panel and the capacity associated with that specific sample. We want to sample not the original characteristics of the structure, because that would defeat the purpose. We want to sample directly the characteristics of the surrogate, but we want to do it in a way that preserves the correlation between stiffness and capacity. And that requires a good amount of thought. Now, these results are have been submitted in papers. We will present a number of them at the EMI and ICOSAR conferences this summer. I would just draw a few conclusions. First of all, creating models of power and transmission lines requires a lot of nuances and a lot of advanced work on these models is still needed. There are a number of groups around the world doing this, and I do believe it's very important that we refine our models. It's important also to understand that this refinement is not perhaps needed to capture each individual structure, but it is important that we capture the variability within a portfolio of these structures. And the possible solution to do this, the one that we recommend, is the use of class fragility functions for these systems. Thank you so much.
Great. Thanks so much, Paolo, for kicking us off. In the interest of time, we're just going to move right along. Paolo, there's one or two questions in the Q&A you can answer, but the next presenter is Seth Guikema from the University of Michigan. And through no fault of his own, Seth has had trouble logging on, although I see him now, so I'm glad to see your face. Thanks for joining us, Seth. You missed at the beginning, but Seth will be the next presenter. And then, Seth, at the beginning, I said that the Q&As will happen in the chat. If you can't see those, we could relay those to you, and you can answer them at the end during the panel discussion if needed. So over to you.
Great, and thank you. Yeah, I'm Seth Guikema at the University of Michigan. I apologize, I'm on by phone, and someone else is going to drive my slides, but we're making this work. So I'm in the Department of Civil, Environmental, and Industrial and Operations Engineering. So next slide. So I'm going to try to summarize an awful lot of work relatively quickly, both on short-term power outage forecasting and then long-term changes in power outage risk due to climate change. This work was funded by a lot of different entities, including a bunch of power utilities, SCE, Southern Companies, AEP, First Energy Consumers, and then, of course, our usual federal agencies. So next slide, and next slide. So one thing that we have been working on for 20-ish years is power outage forecasting for utilities. So this is developing models to predict how bad an incoming weather event is going to be in terms of outages, both spatially where it's going to be, how many total outages. And these are operational models that a bunch of different large utilities have put into practice. They run every 6 hours so they can get their estimates of crew needs, essentially, and to some extent materials, so they can better plan their response. So when we think about this sort of modeling, we have to understand the decision context. I started off working on hurricanes, so I'm going to give that example, though we now work on all weather events. So for a hurricane, when a utility sees a hurricane on the horizon, right, 4 to 6 days ahead of time, that forecast becomes credible. They have some decision to make, and their big decision is crews. A large utility can spend $20 million a day on crews during their restoration. This is their really expensive decision. So somehow we have to get them information about how much damage there's going to be, how many outages there's going to be, so they can start planning these crew requests. So next slide. So on the short term, our goal is to get estimates of power outages 4 to 6 days before landfall. And even in a hurricane, most of the outages are in the distribution system, not the transmission system. So we need to figure out how do we model a distribution system, which is not maintained to nearly the same standard as a transmission system. The tree setbacks aren't as big, and a lot of the outages are due to trees impinging on lines and to some extent poles. So we took a different approach, and we've developed, next slide, predictive models where we use data from the utility and a lot of different spatial information. We've got 25 or so papers on this if you want to get all the technical details, but everything from, of course, the assets that are there in each grid cell, poles, reclosers, overhead, underground spans, circuit breakers, all of that sort of stuff, but also soil type and soil moisture levels are really important. Tree type and tree density are really important. Land cover is really important. Tree maintenance is a critical variable in terms of how frequently they trim the trees, because trees are one of the main drivers of outages during anything that's a wind event, a hurricane, a thunderstorm, anything like that. So next slide. So at a high level, I'm going to give the hurricane example here. At a high level, we get data from historic hurricanes and what happened in their system in terms of number of outages, number of broken poles, number of broken cross arms, spans down, underground runs that need to be repaired. We get all of this data together with all these other covariates, and we train statistical or machine learning models to then try to estimate what's going to happen in a new event. For a hurricane, we run our own hurricane wind field model. So we ingest the track intensity forecast, run a hurricane wind field model, and then we use that to train the model. When we go to make a prediction for a new storm, that's pretty fast, right? That we can do the entire East Coast in about 5 minutes on a laptop. So most of the effort comes in this training testing portion. So this is, in a sense, a simulation problem because of the nature of the holdout testing. Next slide. Okay, to do a forecast, we ingest the hurricane forecast. It might be a single track, it might be a full ensemble. We've done the full ensemble from National Hurricane Center and other places. For each one of those ensemble members, we run the wind field model. We then use the statistical model to estimate outages at the grid cell or census tract, whatever version of that model we're running. And that gives us then either a single estimate or an ensemble of impact estimates. So next slide. This is one older one. This was with a utility. They didn't want us to show a map of where they were. You can guess. On the left is Hurricane Ivan. That's the actual outage map. And an outage here is a non-transitory activation of a protective device. So it's someplace they have to send a crew to do a repair. It might affect one house. It might affect 200 houses. This isn't the customer model. We have other customer models. So on the left is actuals. On the right, when we go back afterwards and use best tracks, we eliminate the track uncertainty and then run the model. And we get pretty close that the overall error is pretty small and the spatial error is pretty small. Next slide. We've then done this for a bunch of different storms. One of the first ones that we released publicly was Hurricane Sandy. This was 13 years ago now, kind of surprising. Our graphics were terrible because we were in the process of developing the output as the storm happened. And then our media office, I was at Johns Hopkins at the time, convinced me to do a media release. And long story short, the model was overall pretty accurate in terms of the number of outages. Spatially, not too bad. Overestimated on the southern side of the storm, underestimated on the northern side. Our wind field was more asymmetric than our wind field model was assuming. And this led to an awful lot of media interviews. I think I did like 65 in a week and a half, some of them live. And if you haven't trained for that, that's an interesting process to go through. So if you're a grad student listening to this, I would say, think about how you're going to talk to the media if you're in this space. Next slide. We've run a bunch of other storms, just run through a few. Matthew was an interesting one because it was a storm that skirted Florida and didn't quite make landfall. And this led to a pretty odd wind field, and it taught us some things about our wind field model we were using. So next slide. Just a couple more examples. Of course, Hurricane Irma, lots of outages in Florida. We ran Hurricane Irma and ran it through the event. The one on the right is a smaller storm. This was Floyd in North Carolina. Next slide. So that was all short-term outage forecast. Storm is coming, do a prediction. We've now done that for winter storms, thunderstorms, all-weather models, West Coast, center of the country, a little bit of East Coast. So we've got a lot of different models there, but that's all short-term. We wanted to ask the question, how can we then estimate long-term risk? And this is where it really gets into simulation. So next slide. So when we think about tropical cyclones, again, we're going to talk tropical cyclones here. They cause massive amounts of damage, of course, right? We see these sort of pictures emerging from a lot of these post-events. In looking more broadly at power systems in the US, depending on which data set or which references you look at, somewhere between 78 and 86% of power outages in the US are caused by weather. The majority of that is in the distribution system, because that's the particularly vulnerable portion of the system, particularly for wind events. So next slide. Just click through the next two. I was going to click these. Okay, and well, there you go. So we wanted to look at how might power outage risk change in the future due to changes in hurricanes in a changing climate, right? So there are estimates of how hurricane frequency and intensity may change in the future. There's a lot of different estimates in the literature. Downscaling and generating hurricanes in a future climate is challenging. We'll talk about a little bit about that. And if these things change, then utilities, as they're making their infrastructure investment decisions now, have this challenging decision, right? Because they might be putting assets in the field that might be there for 40 or 50 years. How do they plan for what these conditions might look like in the future? So next slide. So what we did, and this was work that was funded by the US EPA, we wanted to project how power outage risk may change in a future climate, both in terms of frequency of outages and duration of outages. And then a different part of the team looked at the economic impacts of this and how the economics would change. I'm going to talk more about the power side today, not the economic side. So we did this at the census tract level, so we could tie to public data. So we had about 47,000 census tracts. Next slide. Okay, so first, we have to somehow generate synthetic tropical cyclones. We teamed up with Kerry Emanuel, who developed a synthetic tropical cyclone generator under different future conditions. So we took a bunch of different climate models. For each one, we generated 2,000 hindcast storms and 2,000 storms in a projected future at a particular point in time under that climate scenario. Okay, so we have a bunch of different predictors that then we use to generate each storm. So now we generate 28,000 hurricanes that make landfall. So this is 28,000 landfalling hurricanes. For each one, now we run a wind field model, and then we run our power outage model, and we estimate the number of outages and the duration of those outages. So this becomes a large-scale stochastic simulation, because we're going to generate 28,000 hurricanes. For each one, we're going to generate a wind field, and then we're going to generate a power outage map, and then we're going to do some other analysis with it. So next slide. The power outage model we used here is a two-step random forest. So first, and this was based on our short-term work, figuring out what sorts of models actually work well to predict outages. So first stage, we predict, are there outages or not? Second stage, for those that were predicted to have some outages, then we predict how many. Because part of the problem is, even with a hurricane at zero inflated, that we have a lot of areas that don't have outages, so we need to account for that. So again, multiple papers on this if you want to get technical details, or I'm happy to answer questions. Next slide. Okay, so let's look at results. I'm going to go straight to results. These are these climate models we ran. So we have 7 different climate models. And for each one, we look at the difference between hindcast and projected, and then we map that difference. So where things are blue, we have less frequent outages. Where things are red, we see more frequent outages. So go to the next slide, and they'll summarize it maybe better. And then this is when we combine all 7 models. So where we see areas that are hashed, that's where there's strong disagreement among the different climate models in terms of the impacts, meaning some are suggesting it'll get bigger, some are suggesting it'll get less frequent. The areas where it's not hashed, we have agreement, a strong agreement, meaning most of the models are saying the same thing. And if you look at this, the Southeast, Georgia, Northern Florida, Alabama, North Carolina, South Carolina, is projected to have significant increases in outage frequency. And the models all agree on this. But if you look at Texas, the median of the ensemble says we're going to have less outages, less frequent outages, but there's a lot of disagreement. Southern Florida, not too much change, partly because it's already pretty bad there. So there's not a lot of room to increase, but the models do disagree on that too. So once we do this simulation process, then we can start to get some sense of how this is going to look. The rest of this work is then asking, okay, who lives in these areas? Who's more likely to see big increases versus not? Which subpopulations? And there's some interesting trends there that we can talk about later. Next slide. So at a really high level, I was trying to boil it down to just the simulation component of this, right? That if we're going to try to do long-term estimation of changes in risk, we kind of have to do simulation. But we really need to ground this simulation on strong data and deep collaboration and integration with power utilities, because they're the ones that know this system. So I go back to that early slide and said, this work, a lot of it was funded by the power utilities, and we got an immense amount of data from the utilities. And that's, to me, the key thing to making this all work. So I'll stop there and look forward to discussion.
Great, thanks so much, Seth. So we've had two presentations mainly focused on wind or hurricane events, and so we're going to change gears a little bit and now focus on resilience of power networks under earthquakes for our last two presentations. So the next speaker is Ken Hudnut. Ken is the lead in the seismic resiliency program at Southern California Edison. And Ken, if you're there, over to you.
Yep. Thank you, Matt. I hope you can hear me all right.
Yep, we hear you.
Great. I know my camera won't work. That's because with our cyber restrictions, I'm not able to use the installed executable of Zoom. So I'm through the browser and limited in that way. But just please also advance the slides for me if you would. Thanks for the invitation to be here with you all today. And I was actually really delighted to see that many of the people's names that are in this meeting I don't recognize. Some I do. So hello to Grace and Rachel and E.T. And sorry, E.T., I know you were in a meeting recently where you saw a lot of this already. But to those of you for which this is new material, I'll try to keep this at a high level, tell you what we have done, what we're in the process of doing to ensure seismic resiliency of the power grid in Southern California. And I'll also try to bring it around to your roundtable topic of, tools for simulating the performance of power networks. When I think of that, I think of some different tools. Maybe some of these are familiar to you, but for earthquakes, one of the really fundamental tools a lot of utilities use is called U.S. Geological Survey's ShakeCast, which is based on their ShakeMap product suite. ShakeCast allows a user to use a cloud-based implementation, typically, to combine information about the locations of critical facilities. In our case, that's how we use it. And then you can also add fragilities if you have them and are comfortable using that over a cloud implementation and so forth. So there's some limitations in terms of how we operationally utilize it, but we do. So for example, when there's an earthquake that like there was 2 days ago in Southern California, we have all of our asset locations in there and we quickly get a readout by asset class of whether or not we expect there to have been need for sending a person there to inspect in the field. So we use it for prioritization of inspections, essentially. Sarah is a tool that was originally developed in support of Southern California Edison and then refined over the years. We also use it operationally. ShakeHouse is automated, Sarah is semi-automated, and these are tools that are in operational use for real-time response to real-world earthquakes. And we also use those both extensively when we're doing earthquake scenarios for training and exercises, which I'll come to in a moment. Another tool that's in development still, but we are using it for analytical studies currently. We hope to eventually use it in future operational real-time for real-world earthquakes, but it's also a multi-hazards tool. That's probably less well known to all of you, but that's called CHAT. It was developed over the last several years. SCE had a successful proposal to the California Energy Commission that supported the development, and we're continuing to support some ongoing development that is to customize it to our in-house needs. So our overall goal with the seismic resiliency program at Edison is to increase the seismic resiliency of California, but we also recognize that what we're doing here may help others worldwide, and we certainly hope through engagement like this to be able to share what we're doing, and hopefully, as you said at the outset, Matt, the idea is to share recent advancements and foster collaboration, so we're here for that reason too. Okay, so I'd like to frame this brief presentation by talking about a couple of use cases, as we call them. The first being for earthquake scenarios. This is one way in which we use seismic simulations. In the case of when we're doing a big exercise, a lot of work goes into that in advance, and we build a big document called the ground truth that's then used during the exercise by a team of several hundred people to conduct the exercise, and we're trying to simulate realistically what would occur. So where that starts is with accurate ground motion. So we are users of sophisticated ground motion models for specific earthquake scenarios. So we are doing our best when we do a big full-scale exercise. Like what we have been doing is every other year we've done our full-scale exercise at Southern California Edison based on an earthquake scenario. And in the past, we had been using the well-known shakeout scenario, which is a 7.8 Southern San Andreas earthquake. For that, we had been using the Rob Graves model. So that was from vintage 2008. What we've just done in the most recent full scale that was based on an earthquake is we've again used Rob Graves simulations, but we're also in discussions with others that are, for example, the recent peer-led workshop that Grace helped organize and ET was in was with LBNL as well as Berkeley, and we were discussing other simulation methodologies that are now being run on some of the very fastest supercomputers. So we are end users of such sophisticated ground motion models. So that's one way in which we use simulations. Then another thing I wanted to come to is the bottom set of 2 points here, and that is another entire use case we have is really prioritization of retrofit projects. So this is really our investment strategy. So we want to use good analytical tools and simulation tools when we're doing these analyses. We're looking at things like of our existing facilities, which ones would be best to invest in for that future state. And as was just addressed by Seth in his presentation, we're trying to decide which building that we have is worth investing money in as a retrofit now to extend its usable lifetime. And we also, as Paolo was talking about with the transmission towers, we have a lot of those. Many of them have been there for a long time, and we're trying to prioritize any retrofits. It's very complicated to do. So we have to make these prioritization decisions carefully and with good analytical backing. Everything we do, it has to be justified as a business decision, and we need to make that justification through what we call our ramp and rate case, and I'll give citation to that. That's an open source document through the CPUC, our 2022 ramp. You can go access that and see our whole strategy given in detail there. Next slide, please. Thank you. So in that first use case, earthquake scenarios, this is the most recent full-scale exercise that we did. This was based on a doublet similar to the Turkey 2023 sequence and Ridgecrest 2019 sequence in that sense. And California Seismic Safety Commission really had the lead on this, and they worked with California Geological Survey, US Geological Survey, to develop these scenarios. And so Edison got on board and as partners with California Seismic Safety Commission, CGS and USGS, and others here as well, to look at these two earthquakes that you see here as a doublet. Earthquake 1 is a 7.25 on the Newport-Inglewood fault, and then earthquake 2 is a 7.05 on the subparallel Palos Verdes fault. So as I said, inspired by Turkey 2023, really, with the subparallel faulting, a larger than typically expected magnitude aftershock soon after the main shock. So just to give you a little bit more of a sense of what these earthquakes would be like for Los Angeles, you see the population density in that gray overlay, and then the intensities of shaking or MMI contours, and that keys to that top bar, that the estimated population exposure to earthquake shaking bar. And what you'll see at the top of that, like over the violent shaking number, which is in MMI 9, is over 3 million people shaken at MMI 9 or higher. That is 40 times more than in Northridge 1994. So I don't know if some of you were there for the Northridge 94 earthquake. I was. Anyway, that says a lot. And it just gives you a sense of just how severe this kind of earthquake would be. And it's one that we've been looking at individually. This same sequence, the same earthquake 1 was used in the mayor's-led exercise that we did at the LAEMD several years ago. So the Newport-Inglewood event on its own has been looked at and used for full-scale exercises before, but what was new and innovative and inspired by Turkey was really this second event. So a 1-2 hit on what's called the San Pedro Port Complex. So you have the Port of LA, Port of Long Beach adjacent there, and really at the crosshairs of the strong shaking in both of these events. Many of the simulation tools that I'm sure you're all familiar with have limitations when it comes to handling a 1-2 punch like this. So in other words, you'll have damage from the first event inflicted on your assets, your infrastructure, your buildings, and then along comes earthquake 2. Well, how has your simulation tool accommodated that initial event damage in assessing damage for event 2 and so on? And so this is, I think, a well-recognized limitation of many of the existing tools. So I'll put that out there as a challenge to you all that are working on next generation tools. Next slide, please. And now I'll come to use case 2, which is that investment strategy. I'm going to try to pack a lot in here, and I should probably keep it brief, but these 3 points here: intersections, resiliency pyramid, and then natural system and infrastructure system scaling and nonlinearity. But let me start with our mission, which is to provide both seismic safety and reliability of the power grid. So we're trying to provide safety not only for our personnel that are working in our buildings, but also the public that are visiting in our buildings. So building safety is a big part of it. But then also we're looking beyond that. I mean, technically, in terms of our calculations of risk and efficiencies, we have limitations put on how we do those calculations. But we also recognize that there are indirect impacts. So if we can reduce the duration of outage from a big earthquake, that's going to have widespread effects downstream, because so many other utilities and infrastructure systems rely on electrical power. So we certainly recognize that. We may not be allowed to use that in our calculations that are how we argue for our rate case increases and so forth, but we certainly recognize it, and we have calculated, of course, and there are huge huge benefits, needless to say, if we can keep the grid up and running and if we can restore it quickly. So we're always trying to reduce the duration of widespread outage. Where that comes in is in a quantity called customer minutes interruption. All right, so intersections. The idea here is simply that where a lifeline crosses, for example, a fault line, that's a point, and at that intersection point, risk is concentrated. So that's a gross oversimplification, of course. A great example of this successful implementation is the Trans-Alaska Pipeline, where it's intersected the Denali Fault. Geologists and engineers work together as a team to craft a solution. And then when the magnitude 7.9 Denali earthquake happened in November of 2002, not a drop of oil was spilled. And of course, there was an outage for inspection, but other than that, it was a success. There was no environmental disaster. And operationally, the impact was limited. And so using that simple concept, though, of intersections, this is one way in which we at Edison, and we encourage others to do it too, is a simple method: identify where the risk is high. Another example from what I just showed you is at the San Pedro Port Complex, where those fault lines intersect lifelines like the Alameda Corridor, shipping and goods movement. That's another example of a risk concentration point. And all generally, what it all boils down to is that where you can identify those risk concentrations for whatever reason, and it may have to do more with asset criticality, those are the places where you'll find it makes the most sense to invest heavily. So that is, in a nutshell, that's the investment strategy. Find where the risk is high and buy down the risk at those locations. Now that also is explained by this pyramid in the green triangle on the right. So our most critical assets are at the top in tranche 1, as we call it. This is again using CPUC formalisms for our calculations and tranching approach. So most critical at the top, this would be our emergency comm sites on mountaintops, our data centers, our operational centers, our black start generation assets, and so on. And then tranche 2 and on down. So in tranche 1, you'll have all of the bulk electric substations, et cetera. Okay, so that's simply point 2. Moving on to point 3, the natural system we recognize is, so much of seismic phenomenology is power law driven. And so you can just say, well, in terms of the fault system, yes, the San Andreas in our Southern California region is the highest slip rate, but then you've got the San Jacinto and Elsinore faults as well. And so it's really breaking down. There are hundreds of known faults in Southern California. So all of them could be they're kind of, we don't know where the next big earthquake is going to happen. It's not necessarily going to be on the San Andreas. So we need to be ready for anything. But it's that, what I'm bringing up here is that the natural system is nonlinear. And so how we approach the problem, we have to be keeping that in mind. And it's also true of the infrastructure. The power grid itself, as was just addressed in Seth's remarks about how, there's in addition to the transmission system, which is relatively very hardened, There's also the distribution system, the wooden poles and wires at the neighborhood level. We are, we're responsible for all of it. That's the tranche 4, the base of the pyramid in the triangle on the right. So we're trying to do all of that. We're trying to ensure that we're combining safety and reliability with metrics, and then propagating all of our methodology down through that triangle, but also applying this simple idea about intersections where risk is concentrated. And with that, I'll just say a lot of work is going on into this in terms of defining our investment strategy and the rationale for it. Like I said, in our 2022 RAMP Chapter 8 on seismic, but it's an ongoing process, and we're continuously analyzing and re-inspecting facilities to see, okay, after we did this retrofit, now we re-inspect and then put that back into the model, and we're constantly looking at our assets, vulnerabilities, and continually checking our own work as well. So this is an ongoing process, a very dynamic one. And with that, I'll end my remarks. Thank you. Oh, I'm sorry, one more. Excuse me, one more slide. I think that's it. So I just wanted to say about how this is a team effort, team of just a couple scientists and a large team of engineers and many others to do the project management aspects of doing these large construction projects. We're currently running at about a $50 million a year budget. So since 2016, when the program was consolidated across all Edison departments, 2016 through 2024 actual completed project spend was $252 million total. And that was across our bulk electric substation switchyards, as well as retrofitting buildings, focusing on not only our most highly occupied buildings like at headquarters, but also our critical facilities, operational centers, and data centers I mentioned. And a lot of it is really non-structural too. Like we have a large number, as you can imagine, of computer equipment racks throughout all of our facilities at IT comm rooms, and we're doing our best to rapidly work through a large amount of non-structural mitigation as well as structural. And I think with that's the end of my slides. Thanks, Matt.
Great, thanks so much, Ken. Good, we'll move right on to our last presentation, which is a trio. So we have Nikola Blagojevic from Stanford University, postdoctoral researcher there, and then Barbaros, Cetiner, and Sina Naeimi, who are both developers at the SimCenter. So I believe Barbaros is first, so over to you, Barbaros.
The three presentations we saw earlier are some of the great examples of advanced research and active strategies to manage risk-to-power networks. The focus of this presentation now will be to discuss the capabilities within SimCenter that support research in this area. And in specific, we're going to discuss capabilities of four primary tools within the SimCenter capabilities. Namely the R2D tool, which provides a platform for high-resolution assessment of disaster impacts and risk on a regional scale. The Brails tool that automates creating inventories of the built environment for natural hazard studies. The Pelican tool for assessment of damage and losses due to natural hazards. And last but not least, Pyrocodes for regional recovery simulation of interdependent systems. I'll start with the inventory generation bit, which is Brails++. Brails++ provides an automated method to create inventories of the built environment. And currently it supports basically three primary components of the built environment: buildings, transportation networks, and power networks. And the problem of creating inventories of the built environment, Brails basically breaks it down into four primary components. It obtains attributes of the built environment from images. This is for the situations where we don't have databases of certain attributes that are essential for natural hazard studies. If we're talking about buildings, it would be something like first floor elevation. If we're talking about transportation networks, the physical locations of where the components will be. Brails has capabilities to extract attributes from images. In addition to these capabilities, Brails also can scrape data from basically openly available data sets. some of which I'll talk about in a second, and puts them in a form that is meaningful for natural hazard studies. So it's not the raw data that you can find in a data set, but it's in a form that's meaningful for say damage and loss analyses. And whenever Brails cannot extract data from using these two approaches, it can also use statistical imputation to fill gaps in inventories based on data known for other known locations. And finally, Brails also has rule sets, which we call inference engines built into it, that can predict unknown attributes based on a number of known attributes. So this is kind of the statistical imputation approach, but it's more grounded on rule sets that are developed based on experience or prevalent practices. And one thing that's also important to mention is Brails++ is developed by SimCenter, but it's slowly getting to a point where models from other researchers are making their way into Brails++. One of the recent ones that we've actually integrated in Brails+ is the first floor elevation model that was built by a research group in University of Florida. So if you have a model that you're interested in sharing with the community that's meaningful for natural hazard studies, Brails does provide a platform to do so. In terms of the public data sets that are currently integrated into Rails, you're seeing basically all sorts of data sets that are available for all supported assets right now. But in terms of power infrastructure, there's two primary data sets that you can use to create inventories of the power networks. The high field data set, which is primarily for the US, it's a federal data set that's openly available. Brails takes that, parses into a form that's meaningful for damage and loss analyses. And the other data set is available on a more global scale. That's the OpenStreetMap data. So these data sets provide pretty good resolution down to transmission line level, more granularity as in figuring out where the distribution lines are. For a more consistent approach, Brails is also close to releasing a model that is developed by Adarn et al. That uses nighttime images of cities to predict where the transmission lines will be. The image you're seeing here, all the blue lines were predicted using that model. And the red lines, just for reference, are the transmission lines extracted from high field data. And the little red stars, you might not be able to see them very clearly. Those are the substations, again, extracted from the high field data. At the beginning of the presentation, I shared QR codes in terms of for how to access these tools. In terms of how you can use Brails++, you really have two options. It's either a Python command line interface, and the QR code will get you to the GitHub repo for that. And Brails++ is also built into the R2D tool for a seamless sort of integration into damage and loss analyses. So those are the two options you have for accessing Brails++. And with that, I will pass it over to Sina.
After that, we had the asset inventory generated by Brails for power distribution network. It was a time that we had. It was a chance that we had to integrate the damage and loss modeling of these assets into R2D. So that's what we did using the HAZAS methodology. Next slide, please. In order to have the seismic damage and loss assessment for power system in R2D, we used the HAZAS methodology and in R2D. For that, Brails is developed to produce the power inventory assets according to the archetypes that we have in HAZAS. Those are generations, substations, and circuits. Generations are basically the power plants that we have in the power network. They produce the power. Circuits are basically whatever assets that helps to bring the electrical power from the generations, from the power plants to the users. And then substations are the facilities that modulate the power in order to bring their voltage down or up, and also like to distribute the power into a neighborhood or to a significant large user. These archetypes are defined by Hazes, and Brails can produce these an asset an asset inventory generated based on these archetypes, and other specific parameters that are needed, and according to Hazes are either actually produced by Brails or assumed inside R2D. And then we need fragilities that estimate the probability of damages. These are in Hazes based on PGA, and that is right now integrated into Pelican. Pelican is right now more than capable to do that, and these are what we have right now in R2D. However, after that, we have a loss and a recovery in Hazes, which is like based on time, on initial damages. We have not integrated that in R2D because we want to have something, and actually we have something better than that, and we are going to talk about that on the next slide. And for that I have to pass it to Nikola.
Thank you, Sina. So once we have the inventory generated by Brails and we have the damage assessed by R2D, then we can simulate recovery from this damage. And this is what I'll be talking in the next couple of slides. Next one, please. So the reason we're talking about recovery is that we want our systems to be resilient to natural hazards. And when we talk about resilience, basically we're talking about the ability of a system to quickly regain functionality following a certain disruption. Next slide, please. And what we have been focusing on in engineering for the last decades has been making our systems robust and redundant. And most of our tools are focused on this first drop in functionality. This is something that we can assess. The problem is when we want to simulate recovery from this damage. For that task, we need new tools, and a lot of our research was devoted to developing these tools that can simulate recovery from damage. There are two main issues with recovery. Recovery has to be considered on a regional scale, and it has to include interdependencies between different systems that are recovering simultaneously. Next slide, please. So when a disaster hits, a lot of our components get damaged, and the way these components interact changes. As these components are recovering, interdependencies between them are slowly restored, and they can also change over time. So that's why it's also important to understand that these interdependencies are dynamic, and we need models that can capture this dynamics in how components interact as they're being recovered between different systems. Next slide, please. So the first thing that we need to start with is simulating the recovery of individual components. And the most basic recovery model for a component, let's say a building or a substation or a pipe or a road, will be the one offered by Hazes. This is a single parameter model where the whole recovery is characterized by a single number, the recovery time. And the benefits of this model is that it's simple, but it's also region specific because it's based on past data, and it provides us limited insights. We cannot really understand how we can reduce this recovery time beyond just reducing the damage that this component is exposed to. What we can do with more advanced recovery models is dive deeper into the recovery process. In that case, we can see that recovery actually consists of a sequence of resource-constrained activities. These include damage inspection. In some cases, we need to obtain financing to start the repairs. In others, we need to have a design, the new design of the building. We need to get a permit for a building. And then we need repair workers or a repair crew to repair the damaged asset. All of these things can be done in PyRecos, which is a software for regional recovery simulation that's written in Python, and it's also open source. I also want to mention that PyRecos can also handle Hazes type recovery models. Next slide, please. So the way that Pyrecode's algorithm works is outlined on the left. And what we can do there, we can simulate the recovery of individual components, but we can also capture how they're interacting during their recovery. And the way to do this is by simulating the recovery as a sequence of time steps. We have this for loop, which you can see on the left. And for every time step, which can be a day, a week, or a month, depends on what the user chooses, we have 3 steps. The first thing that we're going to do within one time step is to update component state. What this means is that we're going to look at the component, let's say a substation, and we'll ask ourselves, based on the current state of damage, what can this substation provide to the community, and what are the resources that this component needs to operate and to recover? Once we understand this in this first time step, for all the components coming from different systems, we move on to the next step. The next step is where we capture interdependencies. We do this by distributing resources among components. And if the component's operation demand is not met, we reduce components' capability to provide supply to other components, which might result in cascading effects, which we can also capture in Pyre codes. Apart from operation demand, we're also looking at the recovery demand, and we are trying to understand if the current supply of resources can meet the recovery demand of the component. And then finally, in the third step, we recover these components conditioned on the resources which they obtained for their recovery. Once we finish with the recovery, we step out of this loop and we calculate resilience. Next slide, please. So here I'm going to focus on this second step within the recovery time step, which is about distributing resources. So what we do there for each of the resources which we're looking at, we have a separate flow model. For example, we can simulate how the power flows in a damaged network, how the water flows, or how people move and come back to these communities as they're being recovered. Next slide, please. But for each of these systems, there are very sophisticated models to simulate this flow. And although we tried our best to develop these flow models, we can never be as good as those models developed by researchers who have devoted their PhDs or a lot of their time to developing these models. So what we wanted to do is to provide a flexible way of integrating these advanced flow models into this original system of interdependent systems model. Next slide, please. And to do that, we developed an API, which allows people to plug in their models independently of the other models which are used in the same system, allowing us to mix and match these models for different resources, depending on the data that we have access to or the computational power we have access to. Next slide, please. So the way that this API works is it has 2 parts. There is a model independent part, which we developed and will stay the same. So if you want to include your own flow model, you don't need to change anything about this first part. And then there's a second part called the model dependent part. This is where we need to write new code to integrate new flow models. Next slide, please. So the way that this model independent part works is that first it takes the information from Pyre codes. It converts this information into a JSON file where for every component we have the supply that this component can provide and the operation and recovery demand of this component at this time step of recovery. Next, please. So then this model dependent part has to have a code which will translate this JSON file into model inputs for the flow model. Next. Once the flow model ran and understood which components demand can be met at this time step, there needs to be a script which will then transform this information into something that Pyre codes can digest, and that's the final part of the API. Next. So we applied this to simulate the recovery of the water system, transportation, and buildings on the Alameda Island. Alameda Island is in the Bay Area, close to San Francisco. And on the left, you can see how this recovery looks like. So what you can see here is that Pyre codes can simulate the recovery of different systems at the same time. So let's say you have your power flow model, but you don't have a recovery model for this system. Pyre codes can provide this recovery model for you. Next. So what we're looking at now is how the housing demand and supply changes over time after this earthquake. So we have this initial drop. There is a certain delay time because repairs are usually preceded by certain delays. And then we see around day 200, we have a slow increase in housing supply. And this is because our buildings are now repaired and become functional again, allowing people to come back into the community. Next. And so as we are simulating the change in the housing supply, we can also track the change in the water demand. And this is one aspect of interdependencies. So as you can see on the bottom graph, we see how the water demand dropped and then increased as the housing supply was increasing. So basically when people leave, we have less demand for water. As people come back, we have more demand for water. And here we use an external flow model called REVET, which simulates water flow in damaged networks, which was integrated with Pyre codes through the API, which I just showed in the previous slide. And here you can see that this water flow model identified that in the first couple of weeks after this earthquake, we would have some unmet demand for water. So people that would stay in Alameda, they wouldn't get water in the first couple of weeks. Next. What we can also do, we can also simulate what would happen with the traffic. So we have this interaction between people going out and coming back, and this will impact our demand for traffic. This will impact our origin destination matrices, which we capture in this model. But on the other hand, we also have the issue of damaged roads and bridges and tunnels, which we also capture. And so then we're looking at this interaction between the recovery of the demand and the recovery of the supply for traffic. And this allows us to capture how many canceled trips we would have over time as this community is recovering from this earthquake. Transportation is also important because it allows us to capture access to repair. So if you have your power model and you would like to know whether repair crews can actually reach damaged components of the power model, we can't provide you with that information because we are simulating how the traffic flows in these damaged networks. And so what we have right now, we have a very simple power flow model, and we will be happy to integrate a more advanced power flow model. On the bottom left corner, you have a QR code which leads to the Pyre codes webpage. Example 5 is the example which you're seeing here. You can see all the code that we use. You can see all the information which we used. Pyre codes is integrated into R2D. So if you generate your damage from R2D and you have your inventory for Brails, you can immediately run the recovery in Pyre codes. Thanks.
Yeah, so that was a summary of some of the existing capabilities in SimCenter tools. The next minute or so, we'll focus on some of the upcoming features that are soon to be released. I'll focus on the main one for Brails++. So I've mentioned Brails++ is currently capable of predicting where the power lines and a lot of the components for power networks are based on the data scraped from public data sets. And it's also able to predict where transmission lines are from nighttime images of urban areas. One feature that will be coming soon also is we're going to use basically computer vision methods to predict additional attributes of the distribution system or maybe transmission systems too, based on the feedback we get from the community. One idea is, a lot of these transmission poles we don't really know the attributes for, and they're databases openly available for this purpose. And computer vision can be a great tool for this purpose. You see an example run that I performed, and some of the basic outputs you get from a run like that. And I'll pass it over to Sina to discuss some of the upcoming capabilities in damage and loss.
Thank you, Barbaros. So another aspect of power network damage and loss is the damage and loss that can happen due to wind. And for that, there are possible ways that our presenters have in detail discussed before. We have also a tentative plan to include these damages due to wind for power network as well. As you can see here, there is a structure for that, and that's our plan. Right now, at the left side, on the left top, you can see that Brails is, as I mentioned before, is capable to produce information about towers, substations, generations. These are the archetypes that we will possibly use. However, these are not going to be enough. As just Barbaros mentioned, that we need also to have more information, for instance, about the law, about the power conductors, or other things like the asset angles and etc. either with inference assumptions or maybe even with more information that we can have in the future. We will have this information, and then we will have the event at the event side. We will need to extend some of the features that we already have in R2D in order to have more information. For instance, wind angle. This is something that we right now we do not have. However, we are going to extend it in the future. Our event generating, so we can have this information, maybe also for more time steps if it is needed. And then we need to map these intensity measures to the location of each axis. On the lower left side of the, you can see that we will need to map a wind angle and wind speed of each location to each of these assets. Right now, R2D is doing so. However, for power networks, we will have an elevation, the parameter of elevation. So we have to extend 2D to 3D, 3 dimensions for that. And also we need to project the wind speed to the according to the asset angle, each asset angle. So that would be our engineering demand parameter. After that, we will use Polycon to assess the damages for tower and conductors using fragility curves that are in the literature. Polycon is more than capable to accept any kind of fragilities. And after that, we have these damages. We need to calculate system performance. However, the problem is that the distribution lines, as mentioned by one of the presenters at the beginning, is the most the asset that is most prone to the damages due to wind. And we do not have fragility curves for that. So in the system performance wise, maybe in the component based level analysis, like the one that we proposed here, we will not be able to go very into detailed system performance in very small details. We will just stop at the transfer level. For that, the question of the system performance would be that either we want to do an aggregated level on distribution line, or if there will be more information, for instance, based on what will be the capability of Braille's and what will be the capability in the future, we will have that. But for now, we are thinking about applying an aggregated level, at least for the distribution level. And then there are on the system performance wise, we will use a simple solver to have to see this as the system performance. However, there is something that we call like alternate current, the AC analysis. The AC analysis it can be done by Power Pandas, Math Power, these powerful tools. However, they need tons of more information on demand, on production, on the capacity of each of these assets. This kind of information are not available publicly. So there is no point to put it in R2D while not many can use. So that is our plan to include the damages from include the wind damages from the beginning to the end, and that's next slide, please.
And that just about wraps up our discussion. This slide sort of is what you saw initially. Here are the QR codes for each of the apps we've talked about. One thing that's important to mention here is basically almost all of the Braille's, Pelican, and Pyrocode's capabilities that we've discussed are integrated into R2D. So if you're interested in using them through a graphical interface, R2D could serve as a one-stop shop. But if you're interested in the specific implementation details, or if you're interested in expanding, some of the current applications, we have the QR codes for Rails, Pelican, and Pyrocodes. You can visit the GitHub repos for all of these tools and take a look into them. And that just about wraps up our discussion here, and we're segueing into the round table discussion. Thank you so much for your attention, and have a great rest of your day.
Perfect. So I'm gonna hand it over. I saw a lot of the questions have been answered in the Q&A already. Thanks to the presenters for doing that. And there's a couple more there. So if you're a presenter, have a quick look at those. Barbaros, there's some on Brails. And then I'm gonna hand over to Luis to facilitate the rest of the discussion.
Yeah, great. Thank you so much, Matt. Hopefully, this roundtable gave an overview of the state of art in terms of practice and research in the resiliency of power systems. First, before we prepare some questions, I don't think we're going to have time to go over all of those. But first, I think we want to answer the questions from the people who have been posting on the chat. There is one question from another attendee. I wonder if Ken and others working with utilities see value in developing open source networks, like, for example, those that leverage Brails, when the utilities have detailed information on the equipment and the lines. It seems that the partnerships with utilities are critical. It's about data, how we have data, and how we leverage data that is open source to model power systems. So do the presenters have comments on that?
Can I jump in on that one?
Of course.
Yeah. So this is Seth. I think there's value to both. So I work really closely with a lot of utilities, and you get far more detailed data from them than we can create. But we've also created ways of developing synthetic distribution systems, because there are cases where we want to do risk and resilience assessment in places where we don't have the relationship with the utility. So our approach for creating synthetic distribution systems has been rolled out nationwide by a company, and that lets us get into places where we don't have the relationship with utilities. But where we do, their data is better than synthetic data.
Yeah, I would just add to what Seth just said. So certainly true for us. So a lot of the data that we have that's very detailed on our asset inventory is considered sensitive information that's restricted. So that's maybe explains for people if they were wondering, why can't they access more detailed information? Well, it's kind of a non-starter. And so there is a certain amount of information that is openly available. And you mentioned sources like Highfeld, and there's a requirement through our regulators that we provide a certain amount of information about the grids, so that people that want to connect additional generation assets to the grid have the information that they require to do their investment strategy planning. So, but yeah, as Seth said, that in areas where you lack data and have ways to get it, one example that I think of is with the recent earthquake in Burma, what's also known as Myanmar, the 7.7 earthquake. There was significant impact to the electrical power grid there. Within the last several decades, there's been massive investment from China and others in the grid, but there's still, I would say, relatively limited information. We were able to find quite a lot through open source, through reports and so forth, but that might be one such example where, and I know that the international community is making efforts to develop models of the power grid, even in places where there may be limited information about it.
I have a quick follow-up on that question, if I could. Just one of SimCenter's main goal is to provide resources for researchers, right? So like a playground for people to test their models and compare their models. So in light of that, is how much value is there in us creating tools or providing tools that other people have created to generate infrastructure, so people can test their models even if they're not directly connected with a particular utility?
I could say this, from within the utility, one of the simulation tools that we make use of is it's our way of simulating the actual grid performance, and we use tools that are the same tools that are actually used, the software that's used to operate the power grid. We use those same tools to simulate impacts to the power grid. those are expensive proprietary software tools. And so I think what we see here is perhaps there's lots of room to meet in the middle and to apply the various different simulation tools as we can, and then figure out ways to collaborate. So I would say that that feels like a challenge for, so we do what we can, but we also have limitations. And so one of them I'll mention too is just the very tight cybersecurity restrictions environment that we're in. I'm not able to simply go to an open source code repository, download, install, and run it on the internal machines. And so that's a limitation in terms of how we can make use of openly available tools. But I think it's a great opportunity for partnership.
Oh, that's great. That's very, very interesting. There is another question on the chat. Which natural hazards are known to cause power transmission failure? For example, flooding that compromises foundation stability or combined wind and water loads resulting from hurricanes. I think we covered some of this during the presentations, but if somebody else wants to comment a little bit more on this, we can also do that.
I can say that we have been collaborating in a project with the company that does recovery of these towers, and one of the things that they were very concerned about is the state of the ground, because it can generate, even after the hurricane, failures due to the weakness of the ground itself, right? Ground failures that are exacerbated when the water level rises. So that's a very important point. It stresses the importance also of having a holistic view of the extreme event, not just wind, not just water, but really all the effects of the hurricane. I'll make a plug. A few months ago, we had another one of these round tables, SimCenter community round tables on regional analysis, and we discussed one of these topics, the need to simulate and select scenarios that look at all the hazards, and there should be the video on the website.
Great, thank you, Paul. There is another question. Have any of your studies compared the synthetic networks with actual networks to explore how well they capture the performance characteristics?
Yeah, I mean, in our work, ours was synthetic distribution, right? So we don't do synthetic transmission. But yeah, we've compared our synthetic distribution systems to really detailed topology of real systems. So we had the full topology from some large utilities, and captures the topology really well. We have not compared like electrical properties of lines.
Awesome. Okay, all right. So I have a question, I guess, just to see whether you're interested in this. So I see that there are many ways to model, right, power systems. You can be very high fidelity and do a very refined finite model of different components of the infrastructure network. And there are other approaches that are a little bit more, that are coarser, more low fidelity, I would call it. So in the context of implementing things in SimCenter for the community, where do you think are the trade-offs there for accuracy and speed in terms of how high fidelity we go, in terms of computational power, data we need? Do you have comments on that?
Yes, I think this is a great question, and I'm very, very briefly touched on this in my presentation. I see this trend in a lot of research areas. You start with something coarse, and then you spend a decade trying to refine the models and have a better understanding. And then you step back and you start asking, did we really need all this? At what point should we have stopped, or how farther do we need to go? And I see that this is a question that is being asked a little bit more. Our results, I had a couple of students looking at these problems, and our results show that several aspects, like the ability to incorporate the random fluctuations in the wind direction, the ability to capture the mechanics right and the right failure modes, sometimes local, sometimes multimodal, it makes a huge difference. At the same time, I think it's not very important. It looks like it's not very important when you look at the whole system to have specific knowledge on each individual structure. So like Seth was saying, in many cases, synthetic models or best guess models like what Brails can do could be pretty good at capturing the overall behavior if they're fed with accurate structural surrogates, like good fragilities for the structures.
Thank you, Paolo. There is one comment on the chat. What about very important structures? I'm assuming it refer to the power system, whether there are some critical infrastructure units that we will need to look more carefully. I guess transmission is, towers are very important, but are there other ones that are we need to look structurally more
Can I say
in detail?
something? Hi, can I just add that was my question. What about dams and power plants, nuclear power plants? So transmission is important, but if you lose power plant, that's going to take another 5 years to, so what about those?
So that's a great point. Now, thankfully, those structures tend to be very, very robust. Like so,
we don't know that. We don't know that unless we do very sophisticated analysis. And Fukushima, was destroyed completely, not because of tsunami, but because the internal structure was destroyed completely. So
Fukushima was destroyed because the surrounding power, it overheated because the surrounding power network was not providing cooling. It wasn't really a structural failure of that.
It was. I have recording last year from the inside. They managed finally to put a robot inside. It was a big failure inside. The whole steel structure inside failed, and they were about to explode, and then tsunami came and essentially cooled them down. I can send you reports on that, and I can send you photos, and it just became available last year because they for 15 years they could not put anything in. Anyway, again, I think we need a very sophisticated analysis of important components, of course the whole network, but also important components.
All right. Now, thank you for those comments. I mean, this is very interesting. We're approaching the end, so I want to pass it to Matt.
Oh yeah, just one follow-up on that actually. One thing we are trying to do at SimCenter is to allow for this multi-fidelity simulation. So if you want to use fragility functions for lots of aspects, but you have a very high fidelity model for another, how can we integrate these things? It's something we're pushing towards. It's a big problem, but there's a long ways to go. But I think it's very interesting for power networks as well as other regional simulations. Just in concluding, I'd like to make a couple of quick comments. We partially organized this roundtable at this time because we've developed some on the inventory side and a lot on the recovery side where power networks could integrate with. So it's for a way for us to see what the state of the art is, but also if you're interested in contributing different tools or models you've created for power networks, we're interested in that. And we think there's some value and a lot of opportunity related to R2D and the interdependencies that Nikola mentions, because we're trying to develop high fidelity modeling for various systems. So if we can plug in some of the power simulation tools to that, I think we can better capture these interdependencies. So we're looking to the community to help us drive the needs and what we should be implementing that lots of researchers might altogether use. So if you're interested in continuing that discussion, please let me know. You're welcome to join our working group meeting. And we're as you can see, we're pushing in this direction, but we have a long ways to go at the SimCenter in this. And our goal is really to figure out how to support you all in what you're doing. So please stay in touch. I'd like to thank our speakers. Excellent job. We covered a lot of ground, I think. I think we stayed within power systems, and there's so many topics to discuss, but I think you did a great job at really driving at what are the problems and the challenges that we're all facing together. So thank you so much for your time, and thanks everyone for participating. The video is available, will be available online on the SimCenter website eventually. So thanks everyone.
Thank you.